Hey folks, welcome to the first lesson of chapter 6. We are going to, in this lesson, look at work and energy and power. That's going to be this whole chapter actually. We'll do some conservation of energy, some thermal energy, but for this video we're going to start mainly with work and power. A definition of work in a physics sense, there really isn't a good one. You'll sometimes see people say that it measures effort, but that's actually really not a good definition. The definition for work, it's almost easier to think about it just as an equation, which we'll see in just a moment here. The symbol for work is a capital W. The units are joules, which is a capital J. And work is a scalar, which means there is no direction. So we're not going to have to worry about like north or south or east or west or things at an angle. Actually, I shouldn't say that. You're not going to have to worry about work at an angle, but there are other things you might have to deal with that are at angles. Here's really maybe the better definition. And you can see I've called it definition. It's just the equation. Work is simply equal to force multiplied by distance. The big key takeaway, I want you to put stars beside this, is that your force and your distance, when you're calculating work, they have to be parallel. They have to point in the same direction. So what we're going to do in Physics 11 is we're always going to lock in the force and the distance and make both of them horizontal, or we'll lock them in and make them both vertical. But you can't take a force at an angle and a distance that's straight up and down and just go and multiply them. It doesn't work. They actually have to be pointing in the same direction. We'll see some questions that specifically deal with that issue coming up at you in a little bit. But let's start with something easy. Work is simply force times distance. So let's figure out how much work is done on this crate. You can see somebody's going to push with a horizontal force of 8 newtons. The crate is going to slide to the right 4 meters. You can look at that and say, okay, the force and the distance are parallel. So it checks that requirement. And then it's as easy as multiplying the two together. 8 newtons times 4 meters. There was 32 J for joules. 32 joules worth of work done to that crate. So let's try another example that looks very similar. What about this one? And it might take a second for your head to wrap itself around how this could even be possible. How do you push something to the left and have it move to the right? Well, it actually means it must have been moving towards you. So it was like sliding along the ground, moving towards you, and then you've kind of gone like, whoa, 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 and you're sort of catching it and slowing it down. In this case, the force is actually to the left, so it's negative. It's not a direction. In this case, when we get a work of negative 32 joules, that actually means you've taken 32 joules of energy away from the object. Because the only way this is possible is to make it slow down. And we'll see in the very next video that when things move, they have more and more energy the faster they go. So here, if we've slowed the thing down or stopped it, we've taken away 32 joules. So that negative represents that we've removed energy. It doesn't represent that the work was done to the left. The direction piece doesn't matter because work is a scalar. Let's try some questions that are a little bit more difficult or a little bit more involved, because just multiplying F times D all day long is boring. Here we want to find the work done on the 5 kilogram crate. And this is a fellow here. His name is Joe. He helps us in chapter 7. If we have some time to cover relativity in chapter 7, we'll meet him again. He is, I'm going to throw this in there, pulling that 5 kilogram mass up at a constant velocity. And we want to know how much work he does on that 5 kilogram mass. So what you have to figure out is, hey, you've got the distance already. That's given to us right in the question. That's easy. But what we do have to figure out is what's going on with the force. Because work is force times distance. And this is where we go back to chapter 5. We touch on it a little bit. If he's pulling with a constant velocity, that means he is matching a very specific force. And that force is gravity. So hopefully you can look and go, yeah, chapter 5 taught me that gravity's pulling down on this thing with 5 times 9.8 newtons, which is going to be 49 newtons. And that means Joe is pulling up because this thing is not accelerating, right? Constant velocity means the forces are balanced. The force of Joe, which is the one we want to use when we calculate work, it's also going to be 49 N for newtons. And now you can look and you can say, cool, the Joe force right here at 49 newtons, it's parallel to that 7 meters distance, right? They're both pointing upwards. So there's our little picture. Work is force times distance. Joe is pulling with 49 newtons for a distance of 7 meters. And that gives you a final answer of 343 joules of work done on that box. So a little bit different. We had to calculate some force. Let's try this one. What if he lifts that crate up onto the top of that building or platform, and then he picks it up and he walks horizontally? So this one, again, we have to think about what's going on. We've got this free body diagram. Still a 5 kilogram mass, so it's still 49 newtons worth of gravitational force pulling down. And if Joe is holding the thing up, then the force of Joe, you could just call it applied force, it doesn't matter, is also 49 newtons. And then a lot of times students will go, okay, cool, got the force, it's 49 times 7. Hey, isn't that the same as the last question? Work was 49 times 7, 343 joules. Done. But it turns out that's actually not the right answer. You have to remember that your force and your distance, look at them there, they have to be parallel, right? We made that little note here on this screen. We put stars on either side. I had that highlighted. And in this case, your force and your distance are perpendicular. That's actually the worst case scenario if you're trying to do work on an object. So because your applied force is upwards and your distance is side to side, the answer is 0 joules, OJ. Even though you might get tired carrying that crate, you're actually technically doing no work in a physics sense. So perpendicular, if things are entirely perpendicular like this case, 0 joules. What if you pull at an angle? So this time he's taking the same crate, he's going to drag it by pulling with this 8 newtons of force at an angle, and it's going to drag the crate 4 meters horizontally. So that last example, we saw that your force and your distance, they have to be parallel, and in this case they're not, right? You've got this 4 meters horizontally for D, but then you're pulling at an angle, so this 8 newtons of force actually has some horizontal piece, but it's also got a vertical piece. So what you're going to have to do with these kind of questions when you see somebody maybe pulling at an angle is we have to go all the way back to chapter 3. We're going to have to break up that 8 newtons and resolve the vector. So we've got 8 newtons at an angle of 30 degrees to the ground. We'll switch colors here. So some of that force is horizontal, some of that force is vertical. And if you look, the distance is locked in as horizontal, so that's the force that I'm interested in. I want this one. I actually don't even care about the vertical force. I'm not even going to go find that one. And I've got a 30-degree angle above the ground. So here, right angle triangle, you can run a little bit of trigonometry. It's going to be cosine that gets us the answer we're looking for. So cosine of 30 degrees is equal to that horizontal force over the hypotenuse, which is 8. And I think I actually have this if I just page down. Yeah, we had just called this horizontal, vertical. Sometimes people call it parallel, perpendicular. It doesn't matter. There's your answer. So cosine 30 was that horizontal force divided by 8. We had called it FH. The math is just 8 times cos 30, and you get this horizontal force of just shy of 7 newtons. And now that we've got the horizontal force, we can make it play nicely with the horizontal distance. F times D, you get a final answer of 28 joules. So in that case, the angle didn't work for us because we had to make the force horizontal to match the horizontal D. Let's look at one more example that's like this one, kind of spun on its head. What if Joe picks up that mass and walks up a hill? So this time, it's kind of weird. He's walking at an angle. We still have to think about which direction forces are going. So if you think about holding something in your hands, gravity pulls down. It's still 5 kilogram block, so it's 49 newtons. And Joe is holding this thing up. The force of Joe, or the applied force, is also 49 newtons. And now you can look at that question and you can say, okay, if the force is locked in as vertical, then this 7 meters up a hill at an angle, we actually don't care about that. We need to figure out how much of the 7 meters is vertical, because the force is locked into that direction. So now we're going to resolve the distance. So we've got 7 meters at 30 degrees above horizontal, and we're going to have to break this thing up. Now, some of the distance is horizontal. Some of that 7 meters distance is vertical. Since force and distance have to be parallel, I actually only care about the vertical component of that distance. I don't even want the horizontal component. I'm going to scratch it out. And if you go to run the math, now its sine of 30 is opposite that vertical distance over 7. So 7 times sine 30. Sine 30 is actually a nice number. It's worth 0.5, if you remember that from special triangles. So your vertical distance here is going to be 3.5 meters. And then we can take that and we can multiply by 49. F times D, 49 times 3.5. I get 172 J for joules. There you go. So another question where you had to do some resolution. You had to break something up in order to satisfy the requirement that forces and distances are parallel. Okay, so that's work. Power, very closely related. It is the rate at which work is done, which simply means we calculate work and then we divide by time. That's all. So the symbol for power is a capital P. The units are watts. What? Which is a capital W. And that's actually how light bulbs are rated. So light bulbs are actually telling you how many joules are being used up per second. So like a 100-watt light bulb is using 100 joules per second. We call that 100 watts. So 1 watt is equal to 1 joule every 1 second. Power is also scalar, so you don't really have to worry about direction. Although you may have to resolve things, right? Forces or distances to get the work to then get power. And there's your equation or definition. Power is simply work divided by time. So let's try a couple of questions out here. Let's try this one. We're going to find the power of the horse. And there's kind of a lot going on. I don't know what you're going to do to sketch this. Sorry. Just, I don't know, draw a stick horse. It's all good. This horse is going to lift a 1,615-pound crate, a vertical distance of 5 meters in 49 seconds. So we want to find power. Power is work divided by time. And in this case, we can say, okay, work is F times D all over time. And then hopefully you can look at this question now, and it's kind of like the ones we did earlier where Joe pulled that crate up. And you can say, okay, you could actually almost make this a free body diagram. There's some gravitational force down. And this is kind of a weird one. I'm just playing around with units. I'm a physics dork. This is in pounds. You don't have to know how to do that conversion. But pounds to kilograms is divide by 2.2. So M times G is going to be 750 kilograms times 9.8. Which is, it's going to be something big. 7350. So that's the force, because if we assume the horse is pulling at a constant velocity, which we can make that assumption, then the horse force, if I can call it that, would be that same value, 7350. N for newtons. So there's the force piece. It's nice and parallel with that 5 meters of distance, so we don't have to do anything with angles, which is kind of cool. So the power in this case is 7350. There's your force. It's just the force of gravity times the 5 meters we lift the crate, divided by the 49 seconds that takes. And if we throw all that in our calculator, you get 750 W for watts. Now that's actually kind of a special number. That's the power of the horse. And maybe you know where I'm going with this. It's a bad physics joke. 750 watts is actually equal to 1 horsepower. It's the power of the horse. So there you go. When you look at like horsepower ratings for vehicles, trucks or cars or something, or boat motors or motorcycles, whatever it is, you can take your horsepower, that's how we typically are rating power, and you could multiply by 750, and that's how many watts of power the engine produces. And it turns out if you watch like Top Gear, some of those shows on TV, any show that's British, they actually measure power in watts or kilowatts, not in horsepower. So there you go, 750 watts, 1 horsepower. And let's finish off this lesson with one last question that's very similar to one that you're going to run into when you do your practice. Here we're looking for the power of a boat motor that can provide a force of 1,875 newtons while the boat travels at a constant speed of 72 kilometers per hour. All right, so we're looking for power, which is work divided by time. And we know work is F times D. We can divide by T. And this is kind of cool. They're giving us a force, 1875, N for newtons. And then we kind of get stuck where it's like, all right, they gave us this speed of 72 kilometers an hour, which I don't actually like, to be honest, because I don't like kilometers per hour. Not really as a physicist. But like, how are we going to fit that in there? Now, what's kind of cool is that speed of 72 kilometers an hour. Actually, before we even deal with it, let's convert it into meters per second. It's going to have to get there at some point. So divide by 3.6. I believe that gives you 20 meters per second. And now hopefully you're looking at that going, oh, okay, this is really not that bad. We need a distance and we need a time. And we know the boat is traveling 20 meters every 1 second. So what's kind of cool, if you're ever given a velocity in one of these questions, it's awesome because the velocity is d divided by t. So let's take this one and say, okay, we've got the force in there. The distance, it's going to travel 20 meters in a time of 1 second. Or you could have picked 40 meters in 2 seconds or 60 meters in 3 seconds. It doesn't really matter. Maybe the easiest one was just to do the 20 and the 1. Grab our calculator. We're moments away from a final answer. 3.75 times 10 to the 4 watts. W for watts. And just for fun, I've never seen boat motors measured in watts. I don't own a boat, I can't afford it, but I've got friends with boats, and that's all you need. There's a little life lesson for you. I have seen boats with like big horsepower ratings though, big stickers on the side. So let's take that number and just do this for fun, a little curse of the physicist moment. Divide by 750 watts, because boat motors are measured in horsepower. Hey, there you go, just for fun. That is a 50 horsepower motor. So there's lesson number 1. Done. That's a wrap, or a burrito if you prefer. Try out box number 1 practice. You will find the chapter outline in the All Resources folder. You've got some textbook questions to try out of there, calculating works and powers. So give that a try. And please join me for a Zoom meeting if you've got any questions about this lesson or questions about the practice that's been assigned, or fire me an email, or let me know if you want to do your own little Zoom meeting if you've got a question that can't wait for our regularly scheduled meetings. So I hope to chat with you soon. Have fun playing around with work and power.